Hello, and thank you for watching my presentation on an element map approach to petrology. Igneous rocks contain a record of the pressure, temperature, compositional evolution of magmatic systems, and in many ways reconstructing that is one of the holy grails of petrology, because with those parameters constrained, the dynamics of the system are constrained. However, there's a lot of complexity. Reservoirs are often replenished, leading to mixing between magmas, their crystal cargo, homogenization, assimilation, crystal melt reaction, and also degassing, all of which leads to compositional complexity of the system, which we then find ourselves studying in the igneous rock record. So the conventional approach to reconstructing that history is to do petrography, plus or minus backscatter imaging, and then follow that up by spot analyses on the electron microprobe of selected targets. But there are a number of drawbacks to this approach. First of all, electron microprobe allows you to get really good quantitative spot analyses, but the amount of data you generate is generally fairly limited, which begs the question to the extent to which they are representative of the system as a whole. Especially because some variations in mineral compositions are petrographically cryptic, and so they are easily missed in selecting your targets. Backscatter imaging definitely helps, especially when you study major element zoning on the grain scale, because that shows up readily on backscatter images. It's more challenging to do that across the full sample and for all phases, and it also does not reflect minor elements very well, or if at all, and so backscatter imaging is good for the grain scale, less so for bigger scales and different elements. So if we had a method for measuring the full inventory of an entire sample, that would be really handy. It would circumvent all of these problems and allow us to reconstruct full igneous histories, and that's where element mapping comes in. So advances in EDS detection have now led to systems where you can generate more than 1 million counts per second for the combined major and minor elements, essentially anything in excess of about 0.1 weight% in concentration. And so as a result, those high count rates allow you to do element maps of full thin sections at microscale resolution within a reasonable amount of time. And so we routinely run these sort of maps in Cardiff, an example of which is shown in the bottom right. So I'm going to highlight a few things that you can do with these maps. The first of which is to look at the sort of compositional zoning on a sample scale, on a thin section scale. So this is an example of an olivine gabbro, which petrographically, shown in panel A, is the thin section photomicrograph, shows very little. There's nothing in the way of modal or grain size or compositional variation that's evident in the thin section itself. Then you look at the element map which we generated in panel B, and as you can see, there is significant compositional complexity. You're looking at magnesium in green, iron in red, and sodium in blue. So you're looking at clinopyroxene in green to red shades and plagioclase in the blue shades. And so you can see that there is significant amount of primitive olivine and plagioclase cores in the lower half of the sample, and also the top right corner of the sample, but in the zone here in the middle top, there is a zone of much more evolved compositions with only sort of relict cores which look resorbed of primitive compositions left in that zone. So this is an example of the type of variation on a thin section scale, variations in composition that would be really difficult to reproduce if you only had spot analysis that you chose by looking at the photomicrograph of panel A. The additional benefit as well is that the fact that you have a graphical representation of the variations in composition makes it much more easy to link to underlying processes. So in this case, and I don't want to go into the details, which are in the paper that is quoted there, is that you can link to the process here where you have a primitive cumulus framework with some interstitial melt here in the bottom half. That interstitial melt concentrates and segregates into this more evolved zone, as it flows through it and reacts with the original cumulus framework. And these sorts of interpretations become much more sound and much more readily made when you have images like this rather than just individual spots without this context. So you can apply the same kind of approach to lava. So this is a highly ferric lava with populations of amphibole and plagioclase phenocryst. The color scale is the same, except that we've added calcium in purple to highlight the anorthite zoning in the plagioclase. So you can readily see that there are two populations of amphibole, a green one, which is more primitive, and an orange one, which is more evolved. And by far the majority of the grains are unzoned. But there are a few rare grains of amphibole which actually do record the zonation from green to orange, and so record the whole evolution of the system and potentially the mixing between these two different populations. And finding those one or two key crystals that preserve this kind of history is one of the major advantages of having a map like this. It becomes really easy to pick targets for follow-up study that way. And a similar case is present in the plagioclase, where the majority of grains is sort of plain blue or blue with slightly purple cores, intermediate cores, and only a few grains preserve the full history of higher anorthite cores shown on the top left, surrounded by lower anorthite zones that are present in the majority of samples. So having this full representation of all of the phenocrysts is very important, making it very obvious which crystal records which part of the crystallization history of the sample, and that in itself is very difficult to do otherwise. The element maps are also really useful to look at the inventory of trace phases and their relationships with major phases. In this case, we're interested in the sulfides and their relationships with the silicates. The color scale, again, is the same. We've got amphibole here in green with a bit of red, and we've got blue for the plagioclase. And we're interested in the sulfides in this sample. Well, where are the sulfides, you might ask? There's no sulfur on this map. Well, that's because they're very small. They're only micron to tenths of micron sized. So we're zooming in here and we add calcium to the plagioclase maps to highlight the anorthite zoning. And still, it's difficult to see any sulfides. We zoom in even more, and that's where they are. These purple spots are the sulfides. And not only do you get from the map a full distribution of where they are in the sample, you also immediately see their petrological context. They only occur in the plagioclase associated with these darker red zones, which represent replenishment of the system. So it immediately becomes obvious that these sulfides are associated with a replenishment process. And so studying these processes through element maps provides immediate context to features such as these. You can go one step further and quantify the element maps, and so obtain more than 1 million probe spot analyses, or at least equivalents of that, per thin section. And that provides an even more powerful approach. The method for that is developed in Cardiff and will be published shortly. The associated software to do this, take this step from qualitative element maps to quantitative element maps, will be freely available to the community. So once you've gone through that process, you can generate quantitative mineral maps. So in this case, again, a full thin section of a highly ferric lava with very large variations in plagioclase and anorthite content, different populations clearly present. And then on the right, you see that you can then plot histograms of the compositional distribution, and so derive populations. You can do statistics on those populations to quantify the full history. So essentially, in making these maps quantitative, you can get the full compositional inventory of your sample. You can also get modal data as a function of composition. So you can make phase maps for the different compositional steps that are present in crystals and in the sample. And so look at the evolution of compositions as a function of progressive crystallization, which brings the time element in the PTX evolution. You can then use the histograms and the quantitative data to quantify the contribution of each of the different end members, each of the different steps that you've identified. You could also combine the quantitative element maps with image analysis to obtain relationships between composition or crystal size. And there are a lot more possibilities that you could think of using these sort of quantitative data, which I'm sure you can do for your specific field quite readily. So this is a very powerful way of taking your igneous rock and reconstructing quantitatively the full crystallization history. So I've shown you that an element mapping approach to petrology provides an exceptional picture of compositional variations, phase proportions, and their interrelationships, a full quantitative compositional distribution for your samples. Together, that provides a significant step towards reconstructing the full PTX record of igneous rocks. Thank you.